For dozens of episodes, we have treated the model as math floating in the air, attention MLPs, LoRA adapters, RAG agents, but all of it runs on a physical chip. This stage opens that chip. And it starts with one analogy that will explain almost every performance decision you ever make. A GPU is a stadium kitchen, thousands of line cooks, one conveyor belt feeding them. Whether your model is fast depends on the belt more than the cooks. A CPU is a few master chefs, 4 to 64 very powerful cores, each doing complicated work fast. A GPU flips that, thousands of tiny cores, each doing one simple step, all at the same time. A transformer forward pass is about 90% matrix multiplies, the most parallel work there is. That is the whole reason GPUs run deep learning 10 to 30 times faster than their core count alone would suggest. Zoom in. The GPU is built from streaming multiprocessors, SMs. The SM is the unit that matters. An H100 has 132 of them, an A100 108, a B200 148 per die. Inside each SM CUDA cores, 4 tensor cores, a register file and a little shared memory. The whole GPU is just this one block, copied 100 plus times. Software maps onto that silicon as a hierarchy. One thread is one lane of work, 32 threads run in lockstep as a warp, that is the real scheduling unit, and the term is SIMD. Warps group into a block that lives entirely on one SM and can share fast memory. Blocks group into a grid, one kernel launch. The trap: if threads in a warp take different branches of an if statement, the warp runs them one after another instead of together. That is warp divergence, and it quietly kills performance. Now the part that matters most for LLMs, memory is a pyramid. Registers are tiny and instant. Shared memory and L1 are small and very fast. L2 is about 50 megabytes. And HBM, the main VRAM, 24 to 192 gigabytes, is huge but slow, hundreds of cycles away. Here is the sentence to remember: when a model generates one token at a time, it must stream every weight out of HBM. So your token per second is roughly bandwidth divided by model size. HBM bandwidth is the conveyor belt, and the belt gates the whole kitchen. Let me draw the machine once end to end, because every later episode points back to this picture. We will start with the whole GPU and zoom all the way into one of them. Outer box, the GPU, inside the graphics processing clusters. Call them sections of the kitchen. Each section holds a stack of SMs. Watch one SM light up green. This is the core compute unit. The same block times 132 is an H100. Open the SM. Inside, a grid of CUDA cores, 4 tensor cores. Gold because that is where the matrix multiply flops come from. A register file and shared memory. Now overlay the software hierarchy. A warp of 32 threads runs across the cores in lockstep. A block sits on this one SM. A grid is all the blocks. Pull back and draw the memory pyramid beside it. Registers at the top, instant. Shared and L1 below. L2 about 50 megabytes. And at the base, HBM, the big slow tank. I will animate one token's worth of weights crawling up the belt from HBM through the cores. That crawl is what limits decode speed. 2 rules decide whether a kernel is fast. First, occupancy. Keep enough warps live on each SM that while some wait on a slow memory fetch, others are computing. That is how you hide the hundreds of cycles to HBM. Too few warps and the cores just stall. Second, coalescing. When the 32 threads of a warp read 32 addresses sitting next to each other, the hardware folds them into one wide memory burst. Scatter those reads, and you pay for 32 slow trips instead. And one card does not have to serve one job. MIG, multi-instance GPU, slices a single A100 or H100 into up to 7 hardware isolated instances, each with its own cores and its own slice of memory, So small models and separate tenants share the silicon without stepping on each other. So that is the machine, a sea of cores fed by a memory pyramid whose bottom belt is the bottleneck. And you almost never program it by hand. You call CUDA-X libraries, cuBLAS for the matmols, NCCL for multi-GPU transformer engine for low precision, which raises the question those four tensor cores keep hinting at. How does a chip multiply two whole matrices in a single shot? And how low can the precision go before it breaks? Next, tensor cores and the precision ladder. Thanks for watching. Thanks for watching. Like and subscribe for more videos like this, and I'll see you in the next one.